few grams per minute coming out of the flume, and it doesn't drop lower than that. So basically in subsequent runs, I use that level as the cutoff for the initial period of the experiment. But basically we see this gradual decrease in flux coming out as the bed stabilizes. When we add this pulse of sediment, this supply of the finest grain size class, the mass flux coming out of the flume rapidly adjusts and approximately matches the feed going in. So that adjustment happened much faster than that adjustment. Then when we shut off that pulse of sediment, we get a more gradual decrease in the sediment again as the bed again goes towards a stabilized case. So there's the key point, not a surprise, but the bed and the topography and the channel adjusts so that the flux in matches the flux out, but it does so asymmetrically. You can also look at the grain size distribution coming out. What I'm actually showing is again in green is the total mass flux coming out, but then these other lines are different and in general coarser as you go down, different size classes of sediment coming out. So even though we're only feeding in the finest size class, which is the brown upside down triangles, we get, especially during the augmentation period, a range of sizes coming out, including the coarser size fractions. And so we're entraining sediment from the bed. We're also, since the flux out approximately matches the flux in, we're also depositing some of the finest size class on the bed. So even though the mass flux rapidly adjusted, the actual grain sizes are still kind of changing during that pulse. And that's the main point there, is that during these sediment pulses, you can still get grain size changes on the bed and of the transported sediment.
Sorry, a question. When you look at the start of the figure, the equilibrium, it reaches its equilibrium after about 80 minutes. Mm-hmm. And you say 1 gram per minute is equilibrium. Whether it's after the augmentation,
it's a little higher.
It's a little bit higher, and you can see that it's reaching its equilibrium later.
Yeah.
At a later point. Do you know whether it goes to that?
We should have. Honestly, the real answer there is that with hindsight, we should have run the experiment for longer. I'll still say that it's a similar trend.
Yes.
And also, with zero supply, you're never truly going to get to an equilibrium state. But equilibrium errors very often is getting close to that, close to that state. And I'm always going to argue that we're at least getting reasonably close to that state.
Explanation that it is for every different section. It's a little bit higher afterwards, after the augmentation.
Yeah, I mean the fluxes coming out at the end did remain a little bit higher, and I mean the explanation there is, well, actually hold that for just a second. I'll get to the explanation there. Basically, the explanation there is that adding this pulse of finer sediment reduces the reference stresses, basically the critical stresses needed to mobilize these grains, and so the grains become a little more mobile afterwards. So here I show, so now let's move on from this transported sediment to the actual grain size distribution on the bed. So again, runtime in minutes. This is for I actually don't have it on there, but this is for one of the 12% slope runs. And you can see the here's the initial stabilization period, here's the period of supply, and here's the bed restabilization after that pulse of sediment. And one thing to note is that after the pulse of sediment, the D50 of the bed adjusted to become coarser than it was initially. And so you add a pulse of finer sediment, and the bed then readjusted to become coarser than it was before in terms of D50. We can also see that the D84 size also showed coarsening as well. And this is what, just because it got coarser than what it did before, and the coarsening happened as a result of adding a smaller size, I'm just gonna refer to it as over-coarsening there. Really, the grain size distribution on the bed did get a little broader in the D50, the smallest size, well, not smallest, but the smaller size classes on the bed did decrease, basically representing the fact that some of the sediment that we fed in was still present on the bed in a greater fraction at the end of the experiment. So we see this change in the surface grain size distribution. So such an effect of coarsening in response to a pulse of finer sediment has also been seen in not a lot, but some other work, including this and some other papers by Leonard Sklar and the people who worked on those. And the reason for it is the importance of the size classes on the bed for controlling transport and the size selectivity of that. So when you add smaller gravel to the bed, you increase the mobility of all the size classes. The smaller grains still remain preferentially easier to transport out, and so they ended up preferentially moving out of the flume. So then one is left with a somewhat coarser lag of grains, and especially that coarse size fraction on the bed afterwards. So that's kind of an explanation for also, I think, that relates to the transported sediment coming out as well. We're still able to move more of those coarser grain sizes coming out. So within that, though, and this kind of gets to the initial surface in general, I want to emphasize that even though we tried to do repetitions, there was variations in the response of those repetitions. So here I'm showing 8% slope experiments, and for the two different 8% slopes, unfortunately we did run this first one, experiment one, for a little longer than the subsequent ones. Well, so there was, basically this experiment one did start at a somewhat coarser initial D84 size on the bed. It did evolve to a stable value, and then you had the pulse, and the D84 increased a little bit. The other experiment at 8% slope, started at a slightly lower, or a somewhat lower initial D84, and there was a much bigger effect of over-coarsening there. And we also see in the D50s a somewhat, offset response there. 12% slope, there's also somewhat different responses there. So, within these experiments, we did a repetition, but there was still a somewhat different response of the bed. So, it does seem, and maybe it shouldn't be surprising, but that the bed was initially, it was sensitive to that initial grain size, basically the stable value of grain size that it got to. Now, surface grain size isn't, of course, the only factor of bed morphology. Roughness also matters. That's what I'm going to get to next. So here we can see, these are, within one experiment, some sequential topographic swaths down the center line of the channel, so distance upstream versus elevation. I have offset these profiles just for just for clarity there. What I'm using as a measure of roughness is simply the standard deviation of bed elevations after detrending the topography. So I remove that average bed slope and then look at the standard deviations of the bed. And for those 4 experiments, here's what you see. So we have, again, runtime in minutes, standard deviation of bed elevation, so my measure of roughness. Now the roughness is pretty variable, but in general, it increases and at least goes to something, a little closer to a stable value initially. It generally decreases, but it's pretty variable during the sediment feed period. And then the roughness generally increases afterwards to at least somewhat higher value. So bed roughness changes as well. We can also look at hydraulic roughness, which is, here I'm using a Darcy-Weisbach friction factor. And, rather than a direct measure of the bed topography, is measured from the hydraulic radius, so basically flow depth, slope, and water velocity. And it actually shows a similar trend to the topographic roughness. And if we compare those, here I'm showing bed roughness on this axis versus the hydraulic roughness there. They correlate pretty well with a R squared there of about 0.03. Now, the relation between D84, now I'll say, for steep mountain streams, very oftentimes it's the D84 that's used as a representative measure of the, that matters of the grain size for understanding roughness. Here the correlation between D84 and bed roughness is not as good, or it's still correlated, R squared of 0.59. And you can see with the 8% slope experiments here, an offset in grain size. So for a given bed roughness, there's a bit of an offset in the D84 size. And similarly for the 12% slope experiments, the grain size is also somewhat offset. Just in a sense for completeness, but also because we want to be able to predict hydraulic roughness, and grain size is often used to do so. The relation between D84 grain size and hydraulic friction, it's correlated, R squared of 0.61, but there is variability in that relation. So the next thing I'm going to do is show that, see if the clustering of the coarsest grain sizes might collapse these data a little bit better. Just to show where I am here, moving on, I'm going to talk about, I talked about coarsening and roughening in the bed. I'll talk about clustering the coarsest sizes next. So to do this, I'm using a spatial statistic called Ripley's K function. And basically, here's a paper that used it in the gravel bed river. Basically, I'm just using the red grains, and what it does is basically looks at the distribution of distances from one particle to all the other particles, for all the particles, and compares that to what you'd expect for a random distribution of particles on the bed. So what you'd expect if you had, complete spatial randomness of those particles. As is actually commonly done, I'm not going to directly present the K function, though Ripley's K is how it's usually initially described. I'm presenting a L prime statistic. And basically the way to interpret this is that an L prime of 0 represents that complete spatial randomness. And I'll show some plots next, of course, of this. A value greater than 0 represents clustering at some distance apart of R. And a value less than 0 represents basically the opposite of cluster, in a sense, a more uniform distribution or fewer particles than you expect at a given offset distance r. Now, there's some different ways that are used to determine what you'd expect for complete spatial randomness. And given the long, narrow flume bed, what I'm doing is some, basically 1,000 different realizations, using a random number generator in MATLAB to get a random distribution of particles on the bed. I do impose, because the particles have a finite size, I do impose a minimum distance that the particles can be together. And another important thing here is that I do get a confidence interval on the complete spatial randomness. So here's a plot that shows a little bit of clustering, although honestly not all that much. So we have, R is the separation distance between particles, and here's my clustering statistic. The red lines are actually the 95% confidence intervals on randomness. And so if you're higher than that, there's a 5% or less uncertainty or likelihood that you would get that degree of clustering for a random scenario. This plot is for experiment 2 at 12% slope, which is actually the most clustered. And we can see at relatively small separations, and I'll also point out that the flume width is about 100 millimeters there, that we have looks like some clustering. And if you look at the actual red particles, I realize that's very small for you guys. They do look somewhat clustered there.
Excuse me?
Yeah.
Did you take a picture during the flow, or during the RAM, or did you stop the RAM and take a picture for?
So we had to stop or at least I did stop the flow to take the photos of the bed. I've done some.
You don't use any roughness in the wall?
We did not.
Destabilization of the structures at the end of the flow? Did you observe some destabilization of the structures?
I looked for it and didn't observe it, at least during the periods once it got pretty stable. It's definitely true that the starting and stopping of the flow does add a perturbation.
Because we perform similar experiments, but with and without roughness in the wall, and without roughness, because of the acceleration near the sidewall, you can have destabilization of your structures. We observe this in
I was set up the flume and at least argued that the scaling represents a subset of the overall flume width. But I certainly agree that the sidewalls can influence things. But I didn't see large scale destabilization against the walls during the experiments. So here we can see. So this is actually a plot, equivalent plot, but for the other 3% or the other 12% slope experiment, and basically it shows a lower degree of clustering, at least slightly above. I don't want to make a big deal of that, but close to that 95% confidence bound. Now that doesn't mean that it's not clustered. It just means that at smaller scales, it just means that you can't necessarily say for certain that it's different from what you would occasionally get for spatial randomness. The other experiments had similarly, one of the 8% slope experiments was arguably more clustered at the short distances than the other experiments. So we do see some variations there. 5 minutes. Thank you, Bill. So those plots were just for actually the last time step in the experiment, looking at the clustering, but we can look at the clustering for every time step. And